I hope all of you are doing good. Let's start today's chapter, Set Theory. Introduction. In our previous classes, we have learned the following topics about sets. Definition of a set, methods of describing set, finite sets, infinite sets and empty set. Cardinal number of a finite set, equal and equivalent sets, overlapping and disjoint sets, universal set, subsets and proper subsets, union and intersection of sets and difference of two sets, complement of a set, Venn diagrams, use of Venn diagrams and solving problems. So in this chapter, we shall review the above topics already learned and shall consider the following topics in particular. De Morgan's laws, cardinal properties of sets, distributive laws and use of Venn diagrams in solving problems involving sets. Okay. Words, let's review. Sets. A well-defined collection of objects is called a set. Each of the object is called an element or member of the given set. Well-defined means that given a set and an object, one could decide without doubt that the given object is a member of the set. For example, the set of vowels of the English alphabet, okay, the elements are well-defined, right? Number 2, the set of clever students of class 8. This is not a well-defined set. The word clever is a relative term. Okay, so generally sets are represented by capital letters like A, B, C, etc. while the elements of a set are denoted by small letters like X, Y, Z, etc. Also, if X is a member of a set A, we write X like this. Okay, if X is a member of a set A. So we read this as X belongs to set A, and if X doesn't belong to set A, we write like this. X doesn't belong to set A. Okay. Now, representation of a set. A set can be represented by the following methods. Number 1, description method. 2, roster method or tabular form. 3, rule method or set builder form. Number 1, description method. In this method, a well-defined description of elements of set is enclosed in curly brackets. For example, A, the set of letters of the English alphabet is written as like this. A, then curly brackets, letter of the English alphabet. B, the set of days of the weeks and written as B, and then in curly brackets, days of the week. Number 2 is roster method or tabular form. In this method, we list all the individual elements separated by a comma of the set between curly brackets. For example, number 1, the set of natural numbers less than 10 is written as like this. Okay. The set of months of the year is written is like this. Number 3 is rule method or set builder form. In this method, we write a variable x representing every element of a set satisfying a condition and close it within curly brackets. For example, number 1, we write the set of natural numbers less than 10 as x such that x is a natural number less than 10. And 2, we write the set of months of the year as b is equal to in curly bracket x such that x is a month of the year. Okay, this symbol is read as such that. Okay, now types of sets. Finite set. A set containing countable number of elements is called a finite set. For example, 1, 2, 3. Okay, number 2, x such that x is a letter of English alphabet. These are finite. Okay, finite sets. Infinite sets. A set that contains uncountable number of elements is called an infinite set. For example, set of natural numbers. Okay, set of natural numbers are the numbers, natural numbers finite? No, natural numbers are not finite. Okay, that. Similarly, number 2, the set of integers. Okay, these are the set of integers which are also infinite, right? Next, empty set. A set containing no element is called an empty set, or you can say null set. It is denoted by this. Null set or empty set, or represented by braces. Okay, it is a finite set. For example, A, x such that x is a circle with 4 sides. Can a circle have 4 sides? No, so this is a null or empty set. Okay, B, x such that x is a prime even number, okay, and x is greater than 3. Is it possible? Because there is only one prime even number, which is 2, and 2 is greater than 3. No, 2 is not greater than 3. So it is an example of null set or empty set. Okay. Next, universal set. a set that contains all the elements of sets under consideration is called a universal set and is denoted by either this symbol or U. Okay. For example, if A is equals to in brackets 1, 2 and B is equals to elements of set B are 2, 3 and 4, then set, that is universal set, is 1, 2, 3, 4. Okay. And universal sets are not unique. Okay. Number 2, if A is the vowels of the alphabets and B is equals to P, Q, R, S, then universal set X is such that X is English alphabet is a universal set, right? Next, equivalent sets. Two sets A and B are called equivalent sets if they have the same number of elements or same cardinal number. Okay, that is, and A is equals to NB. For example, A is equals to 1, 2, 3 and B is equals to A, B, C. Both have same number of elements. That is 1, 2, 3, 1, 2, 3. C is equals to 1, 3, 5, 7, 9 and D is equals to P, Q, R, S, T. Both have same number of elements. Okay, so these are equivalent sets. Next is equal sets. Two sets are equal if they have the same elements. Okay, for example, elements of set A is equals to 6, 7 and 8 and elements of set B 6, 7, 8, 7, 8, 6. So here A is equals to B because of element in a set can be repeated, right? Number 2 is C is equals to ABC and D is equals to ACB. So these two are equal, that is C is equals to D, since elements of a set can be written in any order. Disjoint sets. If two sets have no common elements, we say that they are disjoint, right? For example, elements of A are 1, 2, 3 and B, elements of B 5, 6, 7. They are disjoint, okay? Number 2, if A is equals to a set of even numbers and B is equals to a set of odd numbers, then they are disjoint, okay? Overlapping sets. If two sets have one or more elements in common, then they are called overlapping sets. For example, let A is equals to set of natural numbers, B is equals to set of whole numbers. They are overlapping since they have all the elements common except 0. Number 2 is elements of A 1, 2, 3, 4 and elements of B 1, 2, 3. They are overlapping since both have elements 1, 2, 3 in common. Okay. Next, subsets. A set A is called the subset of B if and only if every element of A is also a member of B. So we write this as A is a member of B. For example, A is equals to set of natural numbers and B is equals to set of whole numbers. So here set A is a subset of B, okay, subset of B. If A is equals to 1, 2, 3 and B is equals to 1, 2, 3, 4, 5, then A is a subset to B, okay. This is the symbol of subset, right. Proper subsets. A is said to be proper subset of B if B has, besides the element of A, at least one more element. It is written as like this. For example, let A is equals to 1 and 2, B is equals to 1, 2, 3, then A, like we'll write this like this, okay. Similarly, if C is equals to ABC and D is equals to ABCD, then, right. Now, operations of sets. Number 1, union of sets. The union of two sets A and B is a set of all elements belonging to either A or B or both, okay. See. A union B is equals to what? X such that X belongs to A or X belongs to B. For example, A is equals to 1, 2, 3 and B is equals to 2, 4 and 5. So, A union B is what? 1, 2, 3, 4 and 5. Okay, we will not repeat the number. And number 2, let C is equals to ABC and D is equals to E, F, G. Then A union B is what? A, B, C, E, F, G. Intersection of sets. The intersection of two sets A and B is the set consisting of all elements belonging to both A and B. For example, let A is equals to 1, 2, 3, 4 and B is equals to 2, 3, 4, 5, 6. Then A intersection, this is a symbol of intersection. A intersection B is what? 2, 3 and 4, okay, which are common in both these sets. 2, let A is equals to X such that X is a month of the year and B is equals to X such that X is a month of the year having 31 days. Okay, so A intersection B is equals to January, March, May, July, August, October, December. Okay, because all these months are 31 days. Okay, next, difference of two sets. If A and B are any two sets, then A minus B is the set of all elements which belong to A but not to B. For example, let A is equals to 1, 2, 3, 4 and B is equals to 3, 4, 5. So, A minus B is what? 1 and 2. And B minus A is what? 5 and 6, right? Let A is equals to ABC and B is equals to ADE. So, A minus B is what? A minus B is B and C. Okay, in curly brackets. And B minus A is what? B minus A is D and E, right? Next, complement of a set. If this is the universal set and A is any given set, then A dash is equals to set of elements not in A but in the universal set. For example, let universal set is equals to 1, 2, 3, 4, 5 and A is equals to 1, 2. Then A dash is what? 3, 4 and 5. Okay, and then in next example, let universal set is equals to A, B, C, D and A is equals to A, B. Then A dash is C and D. Let's do exercise 7.1. Number 1, which of the following collections are sets? Number 1, all students of your class, of course, collection of set. All the days of the week, yes, this is also a collection of set. Next, all popular dramas of Indian authors, no. All dishonest traders, no, because dishonest is a relative term. Whole numbers less than 20, of course, this is a collection of set. All poor people of your town, no. All fair boys of your class, no. All letters of the English alphabet, yes, this is a collection of set. All good cricketers, no, good is a relative term, you know. All major rivers of India, no. Okay, so these are the collection of sets. Okay. Next, De Morgan's laws. Following two laws are known as De Morgan's laws and they deal with operations like union, intersection and complement. Number 1, the complement of union of two sets is equal to the intersection of their complements. Thus, for any two sets A and B, the complement of union of A and B is equal to the intersections of complements of A and B. So, symbolically we write it as A union B and is equals to A dash intersection B dash. Okay. So, we shall prove this in the following example. Let universal set is equals to 1, 2, 3, 4, 5, 6, 7. Let A is equals to 1, 2, 3, 4 and B is equals to 3, 4, 5, 6. So, A union B is what? A union B is 1, 2, 3, 4, 5, 6 and A union B dash is 7. A dash is 5, 6 and 7 and B dash is 1, 2, 7. So, A dash union B dash is 7. So, from 1 and 2, A union B dash is equals to A dash intersection B dash. Number 2, the complement of intersection of two sets is equal to the union of their complements. That is, for any two sets A and B, the complement of intersection of A and B is equals to union of complements of A and B. So, symbolically we write like this. We can also verify it as follows. Let universal set is equals to 1, 2, 3, 4, 5 and 5, 6, 7. A is equals to 1, 2, 3, 4. B is equals to 3, 4, 5, 6, 7. Then A intersection B is equals to 3, 4 and A intersection B dash is equals to 1, 2, 3, 5, 6, 7. So, this is 1. Then A dash is equals to 5, 6, 7. B dash is equals to 1 and 2. A dash union B dash is equals to 1, 2, 3, 5, 6, 7. So, from 1 and 2, it is proved that A intersection B dash is equals to A dash union B dash. Okay. Cardinal properties of sets. Following are the cardinal properties of sets. For any two sets A and B, N, then in bracket A intersection A union B is equals to NA plus NB minus N, then in bracket A intersection B. However, if A and B are disjoint set, then N, in bracket A union B is equals to NA plus NB since A intersection B is equals to 0. Number 2 is 2 N in bracket A minus B is equals to NA minus in bracket A intersection B is equals to NA, and N, then in bracket B minus A is equals to NB minus N, in bracket A intersection B is equals to NB, when A and B are disjoint sets. Okay. Third is N in bracket E dash is equals to N. Okay, this is the symbol of universal set, which is also known as epsilon. Okay, and epsilon minus NA or N A plus NA dash is equals to N epsilon. N then in B dash is equals to N epsilon minus NB or NB plus NB dash is equals to N epsilon. N then bracket A union B dash is equals to N epsilon minus N A union B. These properties can be proved with the help of suitable examples. Distributive laws, they are: number one, the union is distributive over the intersection of two sets. It means that for any three sets A, B and C, we have A union, then in bracket B intersection C is equals to A union B intersection A union C. Okay, remember that. Okay. For example, let A is equals to 1, 2, 3, 4, 5 and B is equals to 4, 5, 6, 7 and C is equals to 5, 6, 7, 8. Then B intersection C is equals to 4, 5, 6, 7, 8. B union. Okay, this is B union C and B intersection C is 5, 6 and 7. Therefore, A union B intersection C is equals to 1, 2, 3, 4, 5, 6, 7. This is 1. And A union B is equals to 1, 2, 3, 4, 5, 6, 7. Therefore, A union C is equals to 1, 2, 3, 4, 5, 6, 7, 8. Then A union B intersection A union C is equals to 1, 2, 3, 4, 5, 6, 7. Okay, so 1 and 2. From 1 and 2, it is proved that this is equals to this, right? Number 2, the intersection is distributive over the union of two sets. It means that given three sets A, B and C, we have A intersection B union C is equals to A intersection B union A intersection C. So let's prove this. Let A is equals to 1, 2, 3 and B is equals to 2, 3, 4 and C is equals to 3, 4 and 5. So B union C is what? B union C is what? 2, 3, 4 and 5, right? Now A intersection B union C is what? It's 2 and 3. Okay, this is one. Next, here A intersection B is what? 2 and 3. Okay, and A intersection C is equals to 3, right? Then therefore A intersection B union A intersection C is what? 2 and 3. Okay, this is 2. So from 1 and 2, 1 is equals to 2, we have this law. Okay, next is Venn diagram. Venn diagram is the most commonly used pictorial representation of sets. This idea was first developed by John Venn, an English mathematician. In a Venn diagram, a closed curve figure represents a set and the interior points within this closed curve represent the elements of the set. In a Venn diagram, the universal set is represented by a rectangle and all other sets under consideration by circles or ovals within the rectangle. Okay. Use of Venn diagrams to show the relationship between the sets. The diagram shows two disjoint sets A and B, as you can see here. Okay. And this diagram shows A and B are joint or overlapping sets. Okay. This diagram shows A and B are joint or overlapping sets, right? This is A belongs to B and B belongs to A. Okay. Here in the above figures, as you can see these figures, the shaded portions show A union B. Okay. And in these figures, the shaded portions show A intersection of B. Okay. As you can see here. And in these figures, the shaded portions show A minus B. Okay. And in these figures, the shaded portions show B minus A. Okay. Example is epsilon 1, 2, 3, 4, 5, 6, 7, 8 and 9 and A is equals to 2, 4, 6, 8 and B is equals to 6, 9. So we have to draw a Venn diagram to show the relationship between the sets. Okay. Since A and B are overlapping, we have the Venn diagrams as follows. Okay. A and B. These two are overlapping sets. Okay. So 6 is common, right, in both sets A and B. So we will write 6 here. Okay. Now 9 and A, we have 2, 4, 6, 8. So we'll write 2, 4, 8 and 6 we have written here. Okay. So here we'll write epsilon 1, 3, 5 and 7. Okay. Example 2 is if NA is equals to 40, NB is equals to 27 and A intersection B is equals to 15 and epsilon is equals to 60. Then we have to find out in A union B. Okay. So we know that A union B for NA plus NB minus NA intersection B. Okay, so NA is what? 40 plus NB is what? 27 and A intersection B is what? 15 minus 15. 40 plus 27 is 67 minus 15 is 52. Okay. Number 2 is NA minus B. Okay, so NA minus B is what? NA minus NA intersection B. NA is what? 40. A intersection B is what? 15. 40 minus 15 is what? 25. Okay, similarly you will do these two parts also. Okay, exercise 7.2. Okay, first question is epsilon 1, 2, 3, 4, 5. A is equals to 1, 2 and 3 and B is equals to 3, 4, 5 and C is equals to 2, 3, 4. Then you have to find. Okay, and remember that always your LHS side will be equal to the RHS. Okay, because there is a sign of equal to. Okay, students, so keep doing practice of this exercise, right? Things to remember. A set is a collection of well-defined objects. 2. The objects, that is numbers or names, etc., used to form a set are called elements or members of the set. 3. The symbol this stands for, belongs to, and the symbol this belongs to, stands for, doesn't belong to. 4. If all the elements of the set A belong to the set B, the set A is said to be the subset of the set B. 5. If all the elements of the set B belong to the set A, the set B is said to be the subset of the set A. 6. While using Venn diagram, remember N in bracket A union B is equals to NA plus NB minus N A intersection B. If A and B are disjoint sets, then N A intersection B is equals to 0 and therefore N A intersection B is equals to NA plus NB. Students, I hope you have understood this chapter. Now keep doing practice of this chapter.